English easy.
Hi, so we have a really fun problem today, which is called maximum space. So I have the formal definition here, but the basic idea is among all Turing machines with a specified number of states and tape characters, someone's raising, on all inputs of size a particular number n, we want to figure out the maximum amount of space that's used. And you can substitute this with time if you wanted to, but we're going to look at space here. So we're going to run this Turing machine for as long as possible. So among all inputs of size n and all Turing machines of a specified type, I want to know the longest running of all of them. And how is this going to work formally? Well, we're going to take the maximum over all Turing machines m with sigma states. So sigma is going to correspond to the number of states. Lambda is going to be the number of tape characters, because the alphabet itself doesn't matter as long as you have the cardinality of it for purposes of this. We're going to take the maximum over all strings w that are of length n. Actually, I should emphasize that this should be length n or less, because a small string might go longer, but it's of all strings of length at most n. And here, what we want to calculate is the space used by that Turing machine, the one we're taking the max over, on that particular input, if the machine actually stops. Because if the machine doesn't actually stop, then clearly it's going to either consume an infinite amount of space or run forever. So we're going to actually emphasize that it stops for this purpose, so that we know that max space of these three parameters is always a finite number. It's never infinite, so there's no issue there. We're going to prove that this thing is not computable. So it's not possible for any program to be given these three numbers and to compute what that number actually is. So you may think, okay, I'm just going to run all Turing machines with this particular type of all inputs of this type and see how long it goes and how much space it uses. The problem is that we will show that that number is not computable. So it's not like you can just wait a really, really long time, because if you could, then this would be a computable number, but we're going to show it's not computable. So let's prove that this is not a computable number. Okay, so let's suppose that this Turing machine C computes this particular function. So it's given these three parameters, the number of states, and the number of tape symbols allowed, and the maximum length of the input. And what we'll do is we will assume that this Turing machine will figure out that number. And what we're going to do is we're going to appeal to the recursion theorem, link up at the card up there, that will allow us to show that this is not actually computable by making a Turing machine that will have an inherent contradiction. So we're going to assume that this is computable and then derive a Turing machine that has an inherent contradiction within it. Okay, so how's this Turing machine going to work? So I'm going to call it Z, and it's going to take some input W. So input string W, which is going to correspond to the length n here. So notice that this W is not actually one of the three things here. It's going to be the length n here, but the number of states and the size of the tape alphabet have absolutely nothing to do with this. So this Turing machine Z only has one parameter, not three, like C does. Well, so we know the length of the input right here. So we can calculate W's length to be n and then pass that number into C and let it do its thing. But we don't have the sigma and the lambda right here. So we're going to appeal to the recursion theorem. So we're going to obtain own description. So the recursion theorem allows us to obtain information about ourselves. So ourselves being the Turing machine, not our actual selves, but it's the Turing machine. So we can actually figure out the number of states and the size of the tape alphabet. And let's actually compute that. So let's let sigma be the number of states in Z, and lambda to be the number of tape characters. So then now all we need to do is feed this information into C, the thing that supposedly computes this thing. So we're going to run C on the three parameters here, so sigma, gamma, and n is going to be the length of the input, which is obviously a computable thing that we can do. So the length of w there. So now let's suppose that this computed number, which we assumed is possible, let's say that it's L. So L is the max space number, whatever that is. So now what we need to do to get a contradiction is to ensure that Z, which is one of these Turing machines that is in this calculation here, we got to ensure that Z actually does more work in terms of more tape cells than this number. And a really easy way of doing that is to move right L+1 positions and then stop. So the fourth step here is to move right L+1 positions and then accept. And this is the contradiction. Why is it a contradiction? Because we can obtain our own description right here, so we know how many states and tape symbols we have. We suppose that we can actually compute this right here. So C figured out, okay, all the Turing machines of this particular type and on this length of input will take at most L cells on the tape, at most. Sometimes maybe less, but definitely at most L. But what we then did was this Z, which is involved in this calculation, must take L+1 cells because it moved right L+1 cells. And so therefore Z takes at least L+1 cells, and so therefore that's a contradiction because Z was involved in this calculation, which contradicts the fact that max space was computable, because if it were computable, then we can make this Turing machine, but it obviously has a logical contradiction built into it, and so therefore we obtain the conclusion that max space is not computable. Okay, so hopefully that was interesting. Leave comments about the recursion theorem or the maximum space used down into the comments down below. I'm always watching them. As always, please like the video and subscribe to the channel. It really helps us out. There are many other links in the video description if you want to support the channel further. And as always, thanks for watching, and I'll see you next time.
That was easy. That was easy. That was easy.